So let me just but yeah, like to access the questions, I suppose we can still use the responders thing. Um, okay, so let me yes, so today's lecture 12. So my plan for today is kind of do a mix of a couple of topics. There are some things that I still wanted to say about what's called discrete probability, which is what we have been doing so far. But I think today we'll have enough time to start moving a little bit more in the direction of what's called continuous probability. By the way, just remember that the exam is next Monday. I guess like maybe today would be like a good place to stop the material for next Monday's exam because there's already enough things to ask. So yeah, probably today would be the last day for topics, and then I'll just work over the week on like a study guide or some practice exams for next Monday's exam. But yeah, I think we have covered already enough. So after whatever I include today, I mean whatever I say today would be kind of like the last stuff for that exam. So okay. The first thing I wanted to mention was let's start with an analogy. So if you remember when you had like a function of one variable, there was the Taylor expansion, right? So the Taylor expansion was, I mean, like like it doesn't matter really where you could do the expansion about with respect to any point, but like, well, under certain hypotheses, of course, as usual, like in all of these mathematics things. But what I'm saying is, like, if you just for convenience, it's sometimes easier to write it with respect to zero. So if you remember the Taylor expansion with respect to zero, this is like it was f of zero plus what f prime of zero times x plus um f double prime of zero divided by 2 times x squared. And well, the next term was with 3 factorial, right, which is 1 over 6. So it was like the third derivative evaluated at 0 over 6 times x cubed. But so and usually like for many things like in calculus already like the first and second derivative give you good information about the function. But if you look at one way to think about the Taylor expansion is that it is kind of breaking the function into something that has it's linear in x, right? So this is linear in x. That means that it just like the power of x, the variable x appears like raised to the power 1, right? This is quadratic in x, right? Because it's x squared literally. And then, I mean, this first term is like x is not present. So it's kind of like, if you want to emphasize that, it kind of looks weird to write it this way, but maybe better for the analogy purposes. You could put like x to the 0. X to the 0 is 1. So obviously that's why no one writes it that way. But if you wanted to put it that way, it is, if you write it that way, it's more clear that the first term is kind of like of 0th order, right? Or a constant independent of x, or in the sense like that the power of x doesn't appear explicitly, right? Uh, so that's kind of like what the Taylor expansion did, and in a way, this is saying that it's kind of breaking like the function into pieces, right? Linear, quadratic, cubic, etc. And then like there is a sense in which when you have like a random variable, right, you kind of can extract information kind of like in pieces in the same way, like a linear piece, a quadratic piece, etc. So when you have like a random variable, which takes values x1, x2 up to xn. So one way to like, for example, what would be you can kind of extract information about x by using like function terms or like expressions which would be like linear in the values xi or quadratic in the values xi and so on. So you can extract information about x using formulas or expressions which would be linear, which would be zeroth order or linear, quadratic, etc. in the variable in the values xi. So for example, what would be kind of like, maybe this is actually the easiest one to think about first. So what would be like the linear formula or the linear expression, or the linear piece of information? So you have x. Oh, what color did I use for the linear term here? I use purple. So what would be like kind of a linear term that you get from x? So we kind of already saw it. There was a formula that we saw which is constructed from x, that where the outcomes or the values that x takes appear raised to the power 1, right? What was that formula? If maybe I'm saying it in a little bit weird way, but there's something that kind of was there was an expression of the random variable that is kind of linear in the values xi, right? What was that? Yeah, the expected value. Good. If you look at the formula for the expected value, right, which was the sum from I equals 1 to n, it is pi times x to the I. So like, if kind of like each x to the I, if you thought about it in some way, like as one of these variables, it is, it is like being raised to the power 1. So it's kind of like it is like extracting like information from x in a linear way, right? Because like every outcome is just being raised to the power 1. Okay, so that would be yes, that like the linear term is kind of the expected value. The zeroth term is a little bit kind of what you would call the zeroth term is, I mean, it kind of makes sense, but maybe it's not how you would think about it. But the zeroth terms are in a sense like the probabilities of each outcome. So that's kind of like what would, like in this analogy, what would correspond to the zeroth term. Because each of these, like, I mean, again, it's kind of like to think about it in a so that it makes more sense. It is like because each pi is kind of pi times x to the 0. You could also think about it. I mean, like in this case, it doesn't make a lot of sense to just like add them all together because the probabilities always add up to 1. So like it could be, it's more convenient maybe to think of them as separate quantities. So this, but I mean, kind of to do like some sort of analogy is like a reasonable thing to say. And then the quadratic term is kind of what like I want to start discussing today. So what's like the quadratic version like of the what's kind of like the quadratic version of the expected value, right? It is really yes, exactly. So there are two ways to think about it. Both are more or less related by formula. So it's more up to you which one you take like as more fundamental. One way to think about it is the variance, and the other way to think about it is the second moment. So the second moment, you'll see in a sec. I'll show you in a second that they are more or less related. So the second moment is literally just what's written as e to the e of x squared, and that's just like the sum of I equals 1 to n of xi squared times pi. Okay. So it's literally just like maybe I should put like the pi's first to just continue the notation. So it's literally just squaring each value of x and like weight each value by the probability and add that together. So it's kind of like an average for the squares, for the squares of the values that x takes. So it's literally that, right? So it's an average of the square values of x, right? So that's one way. I mean, that's kind of like a reasonable thing to think. Well, that should be kind of like the quadratic piece of information from X. The other one, the other close cousin to that is what's called the variance, and that's something that actually ends up being a slightly more useful in statistics and other places. You'll see why in a moment, but it's not unrelated to this second moment. So the other thing that is called the other thing that is kind of like a natural candidate for like the quadratic piece is called the variance. Okay. By the way, the formulas can get a little bit annoying at some point. So instead of calling this e of x, which is kind of like the full name, it's also convenient sometimes to call this mu, like the Greek letter, which is like again like a notation. If you take ever statistics, like a notation that's common for the mean or the average. So this is like the Greek letter mu. So in the variance, what you do is kind of like measure let me write it first like in this notation. You want to kind of measure how much the variable differs from like how far each value of the random variable or each value that the random variable takes how far away is it from the average value, right? So to measure that, like the easiest thing is kind of to take the difference, right? It's just that this difference like could be positive or negative depending on whether like a particular outcome is above the average or below the average. So you kind of want to take every deviation from the average as some sort of like positive contribution to like kind of like an overall deviation or overall error. So the easiest way to fix that is to square it. So what you do is kind of take the average of x minus the mean, the average of the square of x minus the mean or the average value, which in if you prefer like a more concrete formula, what I'm saying is that you kind of take the sum from y equals 1 to n of x of pi times xi minus mu squared. So again, this is kind of measuring how much each value differs from the average value, right? That's kind of like a deviation or error, how much how far away you are from the average value. You square that quantity, and then you do the weighted average. Is that making sense? So this is kind of like each xi is how much the value, and in a particular value of x differs from the average, or from the expected value. Is that making sense? So it's kind of like a weighted like a weighted deviation or weighted error overall change in the function. So you'll see it's kind of again like it is either of these two are kind of reasonable quantities to think they're kind of like the quadratic part of the random variable because they literally involve the squares of the values for the random variable. It's just that kind of here like before like just squaring them you first subtract the average, right? But as you might expect, like they're kind of related to one another, so this like is easy to sort out. And then let's do that. So what's this formula for the variance? Is like the sum of pi I equals 1 to n of pi times x minus mu squared. This is where like you see that it's better to write this as I'm sorry, xi. In this notation, you kind of see why it's better to write this as mu instead of e of x because that just becomes too clumsy. So, but regardless, you can just use like the formula for difference of like the binomial formula or whatever. So this just gives you xi squared minus 2xi mu plus mu squared. Okay, and then I mean you can distribute and separate the sum. So this is I equals 1 to n of pi xi squared minus 2 sum of I equals 1 to n of pi xi mu plus I'm trying to see if I can put all of this together on the same line. So let me just write a little bit smaller. So minus 2. Oh, by the way, maybe I should say like when I'm going to separate the sum, like 2 is like a constant. This is expected value is like a constant. So you can take it out of the sum. So you can take it as 2 mu times the sum of I equals 1 to n of pi xi. And then this one with this one gives you plus a sum of I equals 1 to n of pi times and also sorry like this mu squared is again like a constant, so you can take it outside the sum. So mu squared times the sum from I equals 1 to n of pi. Is that making sense? Like what I did here? So it's just like I'm just breaking up the sum and taking out the constant terms, like ones that do not depend on I explicitly. And then this formula is literally the second moment that I just gave you like a couple minutes ago, right? This is literally the second moment of x. So this, like the first term is just e of x squared, right? What's the other stuff? Well, this is again the formula for the expected value, right? Or the average, or which we're calling mu in this case. So let me put it like as mu in purple. And then you have to use here that the probabilities add up to 1. So you get mu squared. So you get minus 2 mu squared plus mu squared. So you get the variance, right? The variance of x is a second moment minus mu squared, right? Or the variance of x is the second moment minus the square of the expected value, which sometimes is called the first moment, right? So it's kind of like this is also sometimes called the first moment. Okay, so it's kind of like, in fact, kind of like this formula measures, if you just think about it in terms of the notation, this kind of, this formula measures to what extent you can kind of put the two inside how much, to what extent you can change the order of E with squaring, right? So what this is saying is that you actually cannot always like change them, right? You cannot pull out the two. And what measures the difference between the two orders for those operations is like the variance. If you think about it more like in terms of the notation, is that making sense? Questions about this up to this point? So again, the variance, like probably from a statistical perspective, is kind of more like the more reasonable quantity to care about because it's kind of telling you how much the values differ from the average value, and you square those like deviations, right? Average the squares of those deviations.
So what exactly is a moment? Like, why do we call it a moment? Is it like a mathematical thing?
Well, it's just okay. So right, let's see. I actually not like why is it being given the word moment? You mean as opposed to
Yeah.
something else? I'm not 100% sure of like the history of the word, to be honest. Of course, like if you say moment, you think of physics. At the moment in physics, right? Like mass times velocity, but it's not. I would need to like. I don't think there's any obvious like correspondence you can mm, draw there. Like I think moment is more used like as some sort of like synonym with quantity, but yeah, I'm not sure. I'll try to find out like a little bit about the terminology, history of the terminology. It's not. I'm sure like it would have like sometimes you say moment of inertia and things like that also. Uh, so but yeah, here like the moment of the random variable, I think it kind of is trying to draw a parallel with the physics terminology, but I'm not sure if it's just like because sometimes like the words are just repeated because it's convenient to repeat them, and other times it's the words are repeated because there's actually like a connection, right? But at the top of my head, I cannot remember like any obvious connection between the word moment here and the physics terminology for moment. So,
Yeah,
but yeah,
because
there.
in
Mhm.
physics, like torque is like movement of like force, I think. Like
Right, right.
torque.
Yes, like R cross the R cross F, like well, it's the rate of change of angular momentum also. So Yeah, no, it could be like it. I'm sure like the name may have been a rose from there, but I don't know if they took it just because, oh, it's a nice name, let's just repeat the name, or if there was like a closer connection that you can establish. So yeah, but I'll see if I can find something about it, because if there's like a connection that's just interesting to know, but not obvious to me at the moment. Um, so no, but it's like sometimes like it's good to try to find out the origins of the words to see how much of an accident there is. But yeah, at this point, I don't really know, to be honest. Let's do like an example before continuing. So like the easiest variance that you can find is a variance for a Bernoulli random variable. Bernoulli random variable of parameter p. If you remember what that meant that the probability that x would be 1 is p, right? And the probability that x would be 0 was q, right? So like we had found before, if I'm not mistaken, that the expected value or the average, right, which I'm calling now mu, for this Bernoulli random variable, it was just p, right? So we already have this side here. And then for the second moment, right, what's the formula for the second moment is it's just like, again, like kind of like the same formula as before, like for an average. It's just that you're averaging the squares of the values, right? So it's like a sum that it goes from 1 to 2 in this case, because there are only two values, right? So for the Bernoulli random variable, like we could call this the first value and this one the second value, I guess. So this would be p times 1 squared um, plus 0, sorry, plus q times 0 squared, right? So the second moment is kind of fun. I mean, obviously this is not the case all the time. It's just that the Bernoulli random variable is kind of like very simple. And the second moment is giving you p as well, right? So the variance of x, which is the second moment minus the square of the first moment, or the square of the expected value, just ends up being p minus p squared. So you can factorize a p. So it's p times 1 minus p. Or p times q. That's like another way to write it. So for the Bernoulli random variable, it's like a useful formula to remember. So the variance for the Bernoulli random variable is like p times 1 minus p, or p times q. Like either way is how you'll see it written in the literature. Is that making sense? So yeah, in this case, like again, you could think of this as the Bernoulli random variable. The p can go from 0 to 1, right? So for each value of p, you're getting a different variance, right? So for each value of p, the variance is different. The variance is different. So you get like a function of p. So you get a function for this variance. And it's easy to check that. I mean, it's kind of similar to what we did for the entropy last time with the Bernoulli case. But it's like a function of one variable. you can ask, in fact, it's like concave down. You can ask like where it takes a max, and it's easy to check here that the max for the variance is like at p equals 1/2, right? As a max. So what this is saying is that the Bernoulli random variable with largest variance is when the outcomes are equally likely. So Bernoulli with maximum variance is like the fair case, right? Like the is the fair case, or equal where p equals 1 equals q equals 1/2. Which makes sense because in the equally likely case is when there's no preference over any of the two values that the random variable is taking. So that's when the average is that's when you're most spread out from the average. So in the others, there's kind of like a preference for one of the two outcomes. So kind of like that kind of makes it like decreases like sometimes what's called the dispersion, or how much the errors, how much each outcome on average differs from the average value. So it's kind of saying like the most like a variance is kind of like a degree of uncertainty or degree of error, right? So the most uncertainty or error, like it's another way to think about the Bernoulli case with p equals 1/2 as the case with most uncertainty or error. Okay. So make sense. It's like an easy calculation, but it's like a nice one to have in mind. And then you can check, and if you want to try it, it's not too bad. You can check that for the binomial case, which was like n random variables, right? N Bernoulli random variables. So here's an exercise. The variance is just it's just n. It's this multiplied by n. Where n was like in the binomial random variable, you had to do like the experiment n times. So you can either do it by hand. That is not that different from how we computed the expected value for the binomial random variable, or you can just use once we talk about independence of random variables, it would also follow because of the properties of the variance for independent random variables. But I'll delay that conversation for later, so I won't get into that right now. So far, so good. Any questions about this? So the last thing that I want to say for now about this variance expected value stuff is like what their rescaling properties are. So it is very convenient in practice to like just understand how the variance of the expected value rescale under the most simple operation. So expected value and variance on the rescalings. So again, just to emphasize, you have like x, which is like a random variable with values x1, x2, up to xn, right? So the easiest way to rescale a random variable is kind of like to apply what's called like a linear transformation. So you can define for two constants a and b, a b, a new random variable which we will call y, which is just ax plus b. Okay. That's kind of like how would you like, many changing units, typically in physics, that's just changing units, they tend to just be changes of the first form, right? Where say from going from kilograms to grams, like you just multiply by or divide by a factor of 10. There are other changes of units in physics less common, like between Fahrenheit and degrees Celsius, right? Where like if you have seen like the formula, it's not just like a multiplying by a number, it's like there is like the equation of a line, right? So sometimes you do need this coefficient around, but think of in most cases like it's kind of like measuring the random variable in a different set of units. Like that's how to a first approximation how you can think of this new random variable, right? So it's kind of like x, but in a new we're measuring in a different set of units. Is that making sense? So so again, once you have what does this mean? It means that this is like a random variable whose values are what? This is like a random variable with values yi equals axi plus bi. Okay, so that's what it is. Sorry, b is constant, so it only depends on right. So it's very easy to go from the x values to the y values because again it's like a linear function. But again, it's kind of just useful to see what's the effect on the actual values for the expected value and the variance. So let's check first, like what happens with the expected value. The probabilities haven't changed, right? So the probability that y, right? The probability that y is y sub I is literally the same as the probability that x equals x sub I, right? Because they're related in what's called like a one-to-one fashion. So that's the same. So like the PIs are preserved. Okay. And so so let's just do it's like a quick calculation, but it's convenient to do it anyways. So let's just check what's the expected value or the average for y. So here's like a calculation. What's the expected value of y? That's the sum of I equals 1 to n of pi times yi, right? But that's a sum. This is relatively easy. The sum from pi of pi times axi plus b, right? And then you just use like the properties of the sum to break it and to pull out the constants. So this is the sum of a times the sum of I equals 1 to n of pi xi plus b times the sum of I equals 1 to n of pi. But again, this is precisely the expected value of x. And this is 1, right? Because probabilities add up to 1. So this is saying that the expected value of y is just a expected value of x plus b. Or, I mean, it's maybe better to write it explicitly. Like the expected value of ax plus b is a expected value of x plus b. I mean, you could write expected value of 1, but expected value of 1 is 1. So is that making sense? Are there any questions about this? Another way to write this is that mu of y is a mu of x plus b. That's also a nice way to write this. If you remember that mu was the name for the average, another name for the average. So in fact, this is what a very big version of what we will call later, right? That the expected value is like linear, meaning that it is linear in the same sense in which the derivative or the integral were linear. If you remember that from calculus, where when you want to compute it, you can just split it into the sum, right? So it's kind of like the same linearity that you would see in calculus or linear algebra if you have taken linear algebra as well. And then, well, maybe before going on, are there any questions up to this point? So let's, for the variance, we need the second moment as well. So let's now compute the second moment. What's the second moment of y? Well, I guess, yeah, I'm doing it this way. Yeah, you'll see something in a moment. So I will stop writing I goes to 1 to n just to save myself some time. Right, and then you break this again, that's fine. So this is a squared times the second moment of x, right? Plus 2ab times the first moment of x. Plus b squared. Which again, another way to have done that. So here's another way to have derived that if you didn't want to do it like in the cumbersome ways, like to say, well, this is like ax plus b squared, right? And so this is sorry, not A, E of A squared X squared plus 2ABX plus B squared. But now, since we had done in the previous part, that kind of, it's like an extension of what we did in the previous part, that you can really break the E's into sums and pull out the constant. So you get A squared E of X squared plus 2AB E of X plus B squared. So it's kind of the same I mean, it's kind of like the same way to derive it, but it kind of looks maybe a little bit more elegant this way because you no longer need to go through the sigma notation or the sum in order to find that. Okay. So regardless of how you want to get to the formula, you get to this. And finally, what's the variance? Like we just subtract that, right? So the variance of y, which was E of y, the second moment, minus the square of the first moment. Well, if you look at this, it's like A squared E X squared plus 2AB E of X plus B squared minus what's the expected value of y? Expected value of y was A E X plus B squared. Okay, so you get A squared E X squared plus 2AB EX plus B squared. Let me put like the things that I want to have together. So minus A squared E of X squared. You have to be careful here, right? The square, it does matter whether the square is inside or outside the parentheses, right? With the expected value. And then minus 2AB EX minus B squared. So it's great, like a bunch of cancellations. The only thing that survives is A squared times E of X squared minus E of X squared. But that's precisely the variance of X, right? So we get to this formula, which is very useful. You'll see for the rescaling properties that the variance of Y is A squared, the variance of X, or if you prefer, the variance of AX plus B, maybe it's sometimes better to see this formula. It's just A squared times the variance of X. Is that making sense? So on the rescalings, the variance is kind of nice. Adding B, right? Adding B is just a translation, right? So if you think about it, like when you translate something, adding B is kind of adding B to every outcome. So that just shifts like the average by that, everything is shifted by that amount. So the dispersion or like the deviation from the average cannot depend on B, because every value that X takes was shifted, right? So that's why B cannot appear on the right-hand side. And then like what this is saying is that if you kind of change your units, and so just multiply again, like going from kilograms to meters, or like yeah, any, I don't know, any other unit that you would like, then that does that does rescale the overall error by the square of that factor, because everything's like in the variance is like is related to the squares, right? And it is also emphasizing the fact that it is considering every deviation as positive, because even if you multiply by a negative number, right? Even if A is negative, a square is going, like, once you put it in A square, it becomes positive, right? So it's kind of saying that every deviation is being considered positive from the mean. It's not like before when it's not that if you're above the average, then that's positive error, and if you're below the average, it's negative error. Kind of, we want to think of all errors as positive. It's like the most convenient way to do in this case. Is that making sense? So that's kind of the variance of how the variance behaves under translations, which again, it will be useful in a couple of minutes, depending on how much time I have left to get there. So far, so good. Any questions about this? And the last thing left is like, well, the last thing is that, if X has certain, like, just as an aside, before like moving to a slightly different topic. So here's like a final remark. Like if X has units, right? Like if X is like a quantity, right? Like a physical quantity, it X has like some units. Like the units could be position or like joules, whatever, like units of energy or like units of mass, whatever. Then the expected value better have the same units, right? E of X has the same units as X. Which is reasonable, right? Because it's the average of the values that X takes. So, but what's the thing with the variance? What are the units of the variance? You're squaring the units of X, right? So the units of the variance are kind of like the square of the units of X. Is that making sense? So again, you could think that the random variable is kind of like giving you the position of a particle, right? So maybe the particle can be in position 1, 2, 3, 4, 5. It could be in one of 5 positions. The random variable measures, it's like records those positions. It has an average value, which would be like the average position for the particle. Then it's kind of, that will be in units of meters or miles, whatever units you want. And then it's kind of weird to say that the variance, which is kind of like the error, it has units of meters squared or miles squared. So to correct for that, another way to measure the error is to go to one of the most basic things in probability, which is the standard deviation, which is the square root of the variance. So that's why you define the standard deviation, so that you get something back with the units of the of X. So one can define the standard deviation, which is usually called sigma, and that's just the square root of the variance. And that does have the property that it will have the same units as X. Sometimes like the sigma, you either write sigma or write sigma sub X if you want to emphasize the random variable you're talking about. So sometimes you write sigma sub X to say, oh, yes, oh, I don't think, I'm not sure there's actually a Greek letter for the variance. I mean, it's sigma squared. Okay, so like, surprise, surprise, right? Like, so the variance, like, but I don't think it gets like, well, yeah, but they actually don't assign it. I don't think so. I don't think anyone gives like a new name to sigma squared. So sometimes you'll see like the variance written as sigma squared. Okay. But But the way I introduced it, kind of like the variance was like the most important concept, and then I'm taking like the square root of that. Here, like if you write it this way, it's kind of like you're starting from the standard deviation and you square that and you get the variance. Of course, like both points of view are the same. I mean, either point of view is fine. But I'm just saying it is psychologically more, I think it's more easy to kind of start from the variance and then just take its square root because of this unit issue. The fact that the units are not correct, in a sense. And then they've called that the standard deviation. That's, I mean, the standard deviation again is kind of like the you'll see like the variance, kind of like the variance and the average are really, really important quantities of a random variable in the same way which the first derivative and the second derivative are really, really important quantities of a function, right? Like that's why in calculus, most calculus courses, if you think about it, they are spent like only talking about the first and second derivatives. There's not a lot of digression on what the third derivative is and the fourth derivative is. Like a lot of information is already contained in the first and second derivatives. So the analog of that is like, you know, the expected value and the variance, and so they kind of give you a lot of stuff about the random variable. And just to another thing that has like the variance has as a nice property is that when you take square roots, when you take square roots here, right, to get when you take another nice property of the standard deviation is that if you take square roots here, right, then that you're taking the square root of a squared, so you just get the absolute value. So this rescaling property, another way which is usually written out, like is that a like the standard deviation of ax plus b is just the absolute value times the of a times the standard deviation of x. So this is kind of like this rescaling property that we just listed for the variance, right? But in this case, it is useful to have like this more specific notation because you kind of need to know which to the standard deviation of what you're referring to. So if you just call it sigma, then you get confused because there are two sigmas here. One sigma is for x and the other sigma is for ax plus b. So you have to be a little bit careful there. And so that's why sometimes this is like a superior notation, but it can be a little bit over the top. It depends on the context. If you're working with more than one random variable, then it is a useful notation to have. Okay, is that making sense? Okay, so let's take this is more or less what I wanted to say about the average value in the standard deviation or the variance for now. And so what I'll do now after the break is move to a new topic, which is continuous probability. So this, I think, is a good place to stop in terms of like the material for the exam on Monday. So when I come back, I'll start on a different PDF. So this is like end of material for second midterm. I think we already have enough stuff. So yeah, but I'll do it I'll write it on a different PDF so that it's not confusing. So once we come back, yeah, essentially it's chapters 3 and 4 if you are following the book, basically. Again, like there are certain things in the book that I'm kind of skipping over, so I'll just tell you what you can pay more attention to or not. But yeah, I think 3 and 4, like all this conditional probability stuff is already a lot of stuff. And with the discrete probability, then you can ask many questions. So, but yeah, like kind of less than chapters 3 and 4, but not more than that. So yeah, but yes, I was saying, let's just take a mini break, and then when we come back, I'll start a different topic about continuous probability. Okay, so as I was saying, it's a good place to switch topics a little bit or generalize what we have been doing to what's usually called continuous probability. And this is kind of like the part of the course where like most of the tools of calculus come in. So this is like the more like calculus, like the combinatorics stuff that we did earlier does have like a very distinct flavor from the stuff that comes now. So it can be good or bad depending on what your preference is. But yeah, this is more like calculus heavy than compared to the first part. So more like calculus oriented. I mean, calculus was before, like in certain things, like when we were computing, like we were working with series and things like that, like a little bit on when we were talking about the certain random variables, but it was not the same as now where we would be using integrals and all sorts of things. So what's the idea here? Like so today I will just kind of give you like a quick introduction to the continuous case, and then next time we'll talk about like the basic formulas, uh, basic random variables in this case and things like that. So you can think about like here's an example, like a particle. So imagine that you had like a particle, right? You have a particle that can be somewhere along this segment, but on this segment you kind of have like some walls or some partitions, right? So you have like box 1, box 2, box 3, box 4, box 5, box 6, right? So in what we were doing before, like in the up to now, was I say, well, maybe we have a random variable that gives you the box in which the particle is, right? Which corresponds to where the box is, to the box in which, sorry, to the box in which the particle is. So in this case, I mean, if you only care about the box in which it's located, then there are like 6 possibilities, right? 6 boxes, and so there would be 6 probabilities, right? But then and 6 values for x. But then now imagine that you kind of so yeah, let me draw like a particle or like a ball somewhere, like representing where the ball could be located. But then like you could delete the wall or delete the partition and just work with the line segment, right? The entire segment. So now this is a segment of length L, right? And so like instead of like talking about the boxes, because they're no longer, there are no more boxes to talk about, you can just like have like you could literally just be measuring the position of the particle with respect to some reference point, right? So you could have like the ball again here, and you have like some reference, so like kind of like an x-axis, right? So which is like x is like the position of the particle. So like the random variable now x, like what makes sense to what makes most sense in this case is to say that the random variable would be like it's kind of the particle could be anywhere, so it's like a random variable. So it's like the random variable representing the possible positions of the particle, right? But the thing is like because now there's no divisions or anything else, like the particle can be anywhere on this interval, right? So it could be anywhere on the interval from 0 to on the interval 0, right? So it would be anywhere, any number. So the outcomes are all the numbers x on the interval 0, L, right? The outcomes, instead of calling the outcomes x1, x2, x3, you can no longer do that. You just have to use like a x itself, right? Or well, in lowercase, right? So the outcomes are just the axis, right? The different axes, so or is any x on the interval 0, L. Is that making sense? So far, so good. Any questions about this? So the first thing to realize is that the question of what's the probability, right? This is like what becomes a little bit problematic here is what should this be, right? Right. So this is kind of saying what's the probability that the position, right, is the position of the particle is the particular value x, right? So this should be the probability but there's kind of like I don't know how obvious it is, but there's like a big obstacle when you just try to say the probability that the position is like 3 meters or 5 meters, like some like specific exact value. What's the problem? What do you think? What the problem is in this case?
Is it just 0?
The thing is, right, like kind of like you are kind of almost forced to say that the probability should be 0 because whatever number.
Because like, is it because like the interval is just infinitely long?
Not infinitely long necessarily is the word, but infinitely many points. Right.
Yeah.
Right. So the problem is like imagine that you want to give you want to say that for 3 meters, right? Let's say that you want to say that probability for 3 meters is like 1/3 trillion or whatever. Like you can imagine giving it like a super small number, but then especially in the case of an interval, that makes a lot of sense. If you knew nothing about the particle, right? You would like to say, well, each point is equally likely, like for example, something along those lines. And there's not like a really good way to say that if you have to divide 1, right, which would be total probability among infinite many options, right? Because in a sense, 1/infinity is 0. So it is not so clear, it's not so clear how to kind of like assign a non-zero probability in that case. And a more like experimentalist point of view to think about the situation is that in reality, you can never assert, that the probability that the position of the particle is exactly 3 meters. There's kind of like a clear distinction between like something discrete or finite, like saying you're in one of 6 boxes. That's like a yes or no question, like it's kind of like easy to determine that, like empirically, but you cannot really determine that you cannot really determine exactly that the position will be 3 meters or like 3 feet. Like the most you could say is that within a certain range, right, the position is 3 meters plus or minus some error, right? So like the point of view, the approach to take, which is more convenient, is not to try to assign probabilities to individual points, right, or individual values, but more like the probability that that the particle is kind of located in a certain interval. Okay, so instead of like trying to like assign a probability to do a single outcome, we'll say, well, I want the probability that the position is between 3 meters and 3 meters plus minus like 0.000013 meters, and that would be better. So kind of like just to make it more pictorially, you can think of your favorite value of x surrounded like in a cloud of uncertainty. I mean, you can put it in different ways, but so since you can never be 100% sure of what the value x of your position, maybe you say, well, it's between x and delta x. Okay, so here you have x plus delta x. And so you can now you want to talk about something more like this. So this will so I should have written this like so the long story is like this kind of ends up being 0. So what's more useful is something like this. It's something like the probability. In fact, if you wanted to, we can make it a little bit more symmetric. Yeah, maybe it looks nice, more elegant if you put it more symmetrically. So instead, what we're going to ask for is something more like the following. We're going to ask for something like x being between x plus delta x over 2 and x minus delta x over 2. So it is the probability the position is between the values Is that making sense? So that is kind of more like of a reasonable question because it's asking, well, what's the chance that the position kind of like lies within like a certain margin of error, right? Like, so you no longer are asking for the exact position or the exact value, but the exact position up to certain margin of error. Well, no, okay, so like for practical purposes, you'll see that we will do like I mean, like in physical world, there are limitations because like this Heisenberg uncertainty principle, but that's another story. But like mathematically speaking, in the mathematical ideal world, delta x can be as small as you want, but it just is not allowed to be zero. So mathematically, delta x is as small as you want as long as it's non-zero. So. So as long as the rules will be that as long as you choose like an actual length for the interval, then you're good to go. Like this. What's the length of this interval? The length of this interval is delta x, right? So as long as delta x is non-zero, it can be anything that you want, mathematically speaking. Again, like physically speaking, then there are like other philosophical questions, but that's not it, right? So you can, because like there are like physical limits to how much like the values physical quantity can take, but that's a different story. But yeah, like the idea, like, and you'll see in a second that this is starting to approach the philosophy of calculus. Okay. In a minute. So far so good. Any questions about this? So in fact, like just to continue with this analogy of the interval, let's just say that instead of saying the interval is from 0 to 0L, right? Just call this interval from A to B, like so. So let's call it or AB. And then like here's like here's a usual calculus thing, right? Before, right, when the outcomes were finite, right, with finite outcomes, or even infinite, as long as like you could count them, like the first one, second outcome, third outcome, fourth outcome. What we would have is something like the sum of the pi's, right, from I equals 1 to n was equal to 1, right? So now we want something like that.
Is this maybe we can bring in some integration, perhaps?
Yeah, that's where the integral appears, right? So imagine that you agree that the error that you're willing to tolerate is like delta x, right? So how many you can once you have like a certain amount of length for these small intervals, you can kind of break the bigger interval into pieces of length delta x, right? So in the continuous case, or like our current case, right? What's in our current situation, you would like to say something like, okay, I'm going to start a little bit, clumsy, but like here, like in the current situation, you can break the interval AB into smaller intervals of length delta x. In fact, you can take, I mean, if you want, like, which is typically what you would do, like if you remember, yeah, that's also right. It is a little bit more like subtle point, but it for now, like the way in the continuous case, that's something that will happen. But if the usual interpretation is probability theory is like for practical purposes, it won't ever happen, right? So it's just like it's more like you just would never expect to see it. So so here, like, yeah, if you remember how like the story goes with integration, like you could think, well, I want to divide these bigger interval into say like 10 pieces or 100 pieces or 20,000 pieces. So you just make delta x be v minus a over n, right? So kind of like the analog of this would be as like once you have broken, let me do like a small illustration of this, right? Once you have broken like the longer interval into a first interval, a second interval, a third interval, a fourth interval, blah, 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 blah. So interval 1, interval 2, interval 3, interval 4, right? You just, you can take like, this is a plus delta x, this is a plus 2 delta x, right? Like these are all intervals of length delta x up to you get here. The point is that the analog for the sum condition, the analog for the sum condition is kind of like like these probabilities that we were talking about. Oops. So here the analog would be that these sums for each interval, right? For the probability that x is, let's call these endpoints. Let's call the endpoints like the endpoints of the intervals like xi to xi plus 1 if you want. That x is between xi and xi plus 1. By the way, xi plus 1 is just xi plus delta x, right? Because all our intervals have the length, but it doesn't matter. That should add up to 1, right? That's what you would like. It's kind of like saying like the position, the particle has to be somewhere, right? Like that, because if all this, like again, like now this is kind of like the probability for the particle to be in one of these intervals. So the fact that these add up to 1, it sounds like the particle has to be somewhere. So this is kind of reasonable. But then you do the usual calculus trick. Of multiplying and dividing by delta x. Okay. And if you remember how the story goes, when you take the limit as delta x goes to 0 or n goes to infinity, they're both kind of equivalent, right? So in the limit, when delta x goes to 0 or n goes to infinity, that the sum, because it becomes an integral, that's how you should think about an integral, right? It's like a continuous sum or like a sum for infinitely many things. So this becomes an integral. So you get like the integral from a to b, okay? Delta x becomes dx, right? So this becomes, sorry, let me just do, this will become the integral from a to b. This will become dx. And this has kind of like the flavor of some sort of like derivative because it's in a sense like some sort of ratio. This is what gets given the name of a density function. So I'll tell you more about that next time. But this is what will gets just called the probability density function. So the idea is like now this integral should be add up to 1. So this will be called the probability density function. So what would happen in these cases is that to compute probabilities, we would just integrate them. So like just to kind of summarize what's going on. So in our situation, we'll have like a function called f of x in our case. we will have f of x called the probability density function. And the key property of that density function will be with the key property, the probability that x is between x1 and x2, for example, to use like just some different names, it's just the integral from x1 to x2 of f of x dx. So the way in which we will approach these problems is that most of the time I'll give you like a density function, and then with that density function, you can start computing the probabilities. Like in this case, that the position of the particle would be in certain regions, but in other problems, like the random variable could be the energy. So you could have like again like a particle in a container. So you don't know what values the energy of the particle takes. So the energy can vary continuously. So then there's like this distribution, I call the Maxwell-Boltzmann distribution, for example, that gives you like a function, the density function for like what the energy, the probability that the particle has certain energy. It's just that one depends on the temperature of the gas and other things, which is kind of what I kind of wrote like a discrete version of that on Friday, if you check that part again about the entropy. So, but I'm just saying like, this is where the calculus comes in, because literally the way to compute the probabilities is via integration. So probabilities now will be computed using integrals. So probabilities are now given in terms of integrals. So again, that could be good or bad depending on whether you like integrals or not. Is that making sense? So as I was saying, this I think it's a good place to end. So because my announcement, I guess, wasn't too clear on which problems I wanted you to work on the quiz. As I was saying, I'll just make the quiz available for you to check the problems that I wanted to ask you. But you know, you can submit at a later time. So I'll change the submission time. So think about it like some sort of assignment. So you don't have to submit it right away. I'll change the submission to tomorrow noon, like last time. So that way, in case like you studied the problems I didn't want you to study, then you're not affected. Like if you study the quiz problems, then you can just take it. But yeah, so just use responders to copy the problems. And if you know how to do them, then you can just finish it right away. But you don't have to finish the quiz on responders, right? Because you may just want to take some extra time. So I'll just change the deadline for the quiz. But so yeah, you should have until tomorrow noon to submit it, if that sounds good. So yeah, but except for that, I'll see you tomorrow on Wednesday if there are no other questions.
So I had a question on number 57, like in the assigned problems.
Just give me just like 1 second to change the deadlines before I forget, otherwise it will be a mess. Let's see. And also let me start checking problem 57 because I don't remember what it said. Oh, let's see, 57. There's a small typo in part B. I don't know if that's what you were going to ask me. Or is that not what you were going to ask me?
Yeah, part B was the part I had a question about. What was the typo?
The expected value, the expected value was not. This is so stupid that this is what I computed wrongly. The expected value for this die, tetrahedral dies, is not 19/6. It should have been, or maybe I already changed it. I
Yeah,
think in the
it
previous,
might have already been changed. Yeah.
right. In the previous version, it was 19/12, I believe, right?
Oh, I think currently it's 19/12. Like in this document I'm looking
Right.
at.
No, I'll upload it again, but I should have written 19/6.
Okay, that sounds
And
more right. Because I was computing it. I was getting something completely different. So I was very confused. But okay, that makes sense.
no, once you do that, then it is fine. But yeah, it was so silly because like the expected value should have been the easiest thing to compute, but well, let me upload the new version just to make sure like it doesn't cause any more confusion. So let me put here. Oh, I have to save it. But yeah, is that the only thing you wanted to ask me?
Yeah, I'll just redo it and check. Hopefully it'll work out that way. But that
No,
makes
I think that now should be fine. It's just like, yeah, it was silly, but someone brought it up earlier during the an email. So I was, oh yeah, it was a wrong expected value. So, and then it works. It should work fine. Like I double checked again, and then it's fine.
Gotcha. All right, awesome. Thank you very much.
Okay. See you.
Hello, Professor.
Yes.
I have a question about responders, the submission.
Uh-huh.
I thought we take a quiz and then we submit the paper through Gradescope.
Correct. Yes.
And do we have to submit another for the responders?
No. It's only on Gradescope that you have to submit anything. Yes. It's just
Yes,
that a
so-
response.
Yes, you can.
So it's only that on responders, for example, for this quiz, because I made it an assignment, so quiz in quotes. It's only that if you want to check the questions that I was planning that were supposed to be on this quiz, you do have to go through responders. But for anything that we use with responders is usually just for you during the moment you're taking the quiz or the exam. The uploads are only either on Canvas, like on Gradescope, or a separate assignment, but never like never on the lockdown browser.
I see. Thank you so much.
Is that, yeah, no problem.
Yes. Thank you, Professor.